We're jumping straight in today with a really exciting paper that tackles one of machine vision's biggest blind spots.
Oh yeah, the inability to understand visual analogies.
Exactly. We're looking at relational visual similarity, and it's proposing a whole new way to judge how similar two images actually are.
Right, and the core of this paper, it really attacks a fundamental issue with pretty much every visual similarity metric you use today.
You mean like LPIPS, or even the big ones like CLIP and DNO?
All of them. They are all focused on what's called attribute similarity. So, what an image is, the color, the shape, the texture.
Surface level stuff.
Totally. They completely fail to capture relational similarity, which is the underlying logic, the function, or the analogy between two different scenes.
So we have systems stuck looking at the skin of the apple, not the core.
That's a great way to put it. So they formally define this concept and then deliver a solution. A brand new dataset of over 100,000 images linked by shared abstract logic, not by content.
And that let them train a new metric.
Exactly. A fine-tuned vision language model they use to create a new metric called RelSim.
And what's the immediate impact of that?
Well, RelSim is really the first step toward connecting images based on that deep conceptual structure. It just blows the baselines out of the water when it comes to recognizing when two totally different looking images share the same core idea.
Okay, let's unpack that, because to really get why this matters, you have to understand the gap between what models see and what we see. What's the cognitive science they're referencing here?
So they draw on two big psychological theories. The standard way machines see similarity, what they call attribute similarity, is purely perceptual.
That's Trusky's theory.
Right. You're just comparing shared properties. An apple is like a peach because they're both round, reddish fruits. It's straightforward feature matching.
But relational similarity is much, much deeper. It's based on Gentner's structure mapping theory.
Yes, and that's all about analogy and conceptual abstraction. You aren't just comparing the objects themselves, you're comparing the relationship between the elements within each scene.
That abstraction is the real cognitive leap we're trying to get machines to make.
It is. I mean, with attribute similarity, an apple is similar to a peach. That's low-hanging fruit, visually speaking.
Right, perceptually similar. But relationally, they're not analogous at all. And the paper uses that classic earth-peach analogy.
Precisely. The earth is like a peach, not because it's fuzzy, but because its core, mantle, and crust, they correspond to the peach's pit, flesh, and skin.
You're matching the internal structure, not the appearance.
Exactly. And that requires drawing on world knowledge. And this is where they show how badly current models fail.
Right. Give us that other failure example they use. The one where models trained on billions of images still miss a really obvious conceptual link.
The one with the matchstick and the banana.
Yes.
So you have two completely different processes. A match burning down and a banana ripening from green to yellow to black. Current models just cannot see the similarity there.
Because visually, a burning piece of wood and a piece of fruit are complete opposites.
Yes. The similarity isn't in what they are, but in the logic of a gradual, irreversible transformation over time. To get that, a model has to understand the concept of a process, abstract away the objects themselves, and compare the underlying logic.
And a pure vision encoder, or even CLIP, just isn't trained to prioritize that kind of high-level structure.
Not at all, which is why they realized you need systems that can access world knowledge, which, brings them directly to vision language models.
So this is where we get to the really innovative part.
Yeah.
If you want to teach a VLM to see analogies, you need a data set of analogies, which didn't exist.
Yeah.
How did they solve that?
They had to invent the data format itself, and they did it with this ingenious idea of the anonymous caption.
Okay, what is that?
It's a text description that captures the relational logic of an image but strips out all the specific objects.
So instead of a burning mattress turning black, the caption would be something like a subject undergoing transformation over time.
Exactly that. It uses those placeholders. It forces the description to be about the structure. But like you said, trying to write that abstract caption from a single image is incredibly difficult. Ambiguous.
Yeah, that seems almost impossible.
It is, and that's their key innovation. They generated the captions from groups of images. They started by manually curating 532 groups, each with, say, 2 to 10 images that looked totally different but shared the exact same underlying logic.
So if you see a line of ducks, a line of cars, and a line of dominoes all together,
The shared logic, A sequential arrangement of items just pops out at you. It becomes obvious.
That's a brilliant way to force the system to learn the abstraction.
And this data had to be really high quality. So they started with LARN2B, which is, notoriously noisy. Before any captioning, they did a two-step curation. First, they filtered it.
How do you even begin to filter LARN2B for something as abstract as relationally interesting images?
With machine learning, of course. They took a smaller set of human-labeled examples, some with high-order relational cues and some without, and then they fine-tuned a powerful VLM to act as a filter.
So they taught a model to find images that were likely to contain deep logic.
Exactly. And it worked. It pulled out about 115,000 images, which dramatically improved the signal-to-noise ratio.
And only then did they move on to the anonymous captioning part.
Yes, training another VLM to assign those shared group captions. That data set is the core ingredient for RelSim.
So how did they train the final metric? The objective seems clear, right? You want the visual features to align with the abstract text features.
That's the perfect way to put it. They took a large visual encoder and trained it with the contrastive loss function, which is pretty standard for bringing similar things closer together, to maximize the alignment between the image's visual vector and the caption's logical vector.
So the training essentially embeds the idea of relational similarity directly into the visual features.
You got it.
All right, now for the proof. They take RelSim and pit it against the titans. LPIPS, Dino, LPIPS. How do they actually measure something as fuzzy as relational similarity?
They used an image retrieval task. So you give the model a query image, it finds matches, and then this is the clever part, they used GPT-4o as an automated judge.
So GPT-4o scored the pairs on a scale of 0 to 10 based on the conceptual analogy.
Yep, purely on how well they shared that underlying logic. It gives you a quantitative proxy for human judgment.
And the results? They showed a pretty clear hierarchy, didn't they?
Absolutely. The models that are focused on just perceptual attributes, like LPIPS, they scored the lowest, around 4.5. Dino was a bit better, 5.1.
Fancy fell.
LPIPS, got a respectable 5.91. That was the high watermark for the baselines.
And where did RelSim land?
It sailed right past, scoring 6.77. This really confirmed that its training on abstract logic allowed it to see these high-level links that the others just weren't built to find.
Okay, 6.77 is a definite jump, but I have to ask, is that score enough? I mean, is 6.77 close to human performance, or is this just the best we can do for now?
That is a crucial question. The paper positions it as the state of the art for machines, but they also did a critical ablation study that kind of addresses your point. They asked, if the dataset is so good, why not just fine-tune a standard CLIP model with it?
And what happened when they did that?
They definitely got better. Tuned CLIP went up to 6.02. The data is clearly powerful.
But still well short of RelSim 6.77.
Way short. And this backs up their main architectural takeaway. Relational reasoning, which is all about abstract concepts like cause and effect or transformation, is inherently tied to language. The VLM structure seems necessary to fully encode that kind of similarity.
So language isn't just a label, it's the key to the whole structure.
Precisely. And they didn't just rely on GPT-4o, they also ran user studies, A/B tests, where real people chose which image was a better analogy.
And humans preferred the RelSim results.
Consistently. Preference rates were sometimes over 60%. It's the final check that confirms the metric aligns much better with how you and I actually think.
It's also interesting how they visualize the two similarity types on different axes.
Yeah.
It's not an either-or situation.
That's the real utility here. You can now search for same logic but looks completely different, which is a new analogy, or same appearance, different logic. It just opens up so many new ways to retrieve images.
The applications for this go way beyond just retrieval, right?
Yeah.
This feels like a step toward truly conceptual image generation.
For sure. Take relational image retrieval. You can search by function. Imagine you're looking for creative food plating ideas. You search with an image and a rice ball decorated to look like a cat face.
Okay.
The model now finds other images that use completely different foods, fruit, vegetables, to create a similar anthropomorphic face. It understands the function of applying I-like features to food regardless of the ingredient.
That's way beyond simple semantic search.
Yeah.
And that leads to the holy grail, analogical image generation.
Right. We're not just talking about changing the color of a shirt. This is transferring the core structural idea of an image.
So you could give it a visual pun,
Yeah.
and it wouldn't just copy the style. It would understand the idea of a visual pun and generate a completely new one.
That's the goal. Take the logic of the pun and apply that abstract structure to a totally new scene.
They actually built a benchmark to test this, right? To see if the logic was preserved even when the appearance changed dramatically.
We did. And they found that For human-generated analogies, the RelSim score was super high, like 0.88, while the visual similarity scores from CLAP and LPIPS were way lower.
Which is exactly what you want to see. It proved the logic was preserved while the appearance was discarded.
Exactly. And it also revealed a pretty clear gap in current models. Proprietary systems like GPT-4o Image were consistently better at this logical transformation scoring, around 0.8x compared to most open source models, which were closer to 0.7x.
So there's still a performance gap there. But before we get carried away, where do they admit the method is still a bit fragile?
The biggest one is data scalability. I mean, they created the initial 532 relational groups by hand.
That's a tiny number, really.
It is, and it's potentially biased. To really make this work at scale, future work needs automated pipelines for discovering and expanding these relational concepts.
And they're the usual VLM problems, I assume. Hallucinations, biases.
Of course, if the VLM generates a bad anonymous caption, it poisons the training data. And finally, there's ambiguity. A single image can have multiple analogies within it, and it's hard to make the model pick the one you intended.
So to wrap up, we have RelSim, a really crucial new metric that moves machine vision from just asking what something is to what it does or represents.
It's a way to encode analogy into these systems. We can finally measure how well a model understands abstract visual logic.
But that last limitation you mentioned, ambiguity, feels like a perfect place to leave off.
I think so. The paper shows us how to measure the analogy, but the big open question is how we can control it. How do we use text prompts, or maybe new kinds of interfaces, to explicitly tell the model which relational structure we care about?
Right. If you showed a picture of a peach, how do you say, I want the earth analogy, not the other round fruits analogy?
Exactly. Developing that kind of precise relational control that feels like the next major step in unlocking truly creative and analogous AI.